I work with vulnerabilities analysis quite a bit. And one of the things you need for that is data, but it's often very hard to get hold of the data because it contains sensitive information. So we anonymize it or sanitize it. And I got to thinking about that a little bit, and the result is this talk. We need to share data, and that's not just computer science, it's across the spectrum. Okay? The National Institute for Health says we believe that data sharing is essential for expedited translation of research results into knowledge, products, and procedures to improve human health. The European Commission says something similar, although a little more indirectly. Data-driven innovation is a key enabler of growth and jobs in Europe. The importance of data collected online and generated by the Internet of Things objects and the availability of big data analytics tools and artificial intelligence applications are key technical drivers. And I'll swing back to some issues with big data analytics tools later on in the talk. And finally, the one most direct to science from Karl Popper, who says non-reproducible single occurrences are of no significance to science. So we want people to be able to reproduce our results. And to do that, they often need to get access to the same data that we're using. In fact, psychology is having a huge problem with this right now because many of some of the seminal papers could not be reproduced. So all of this requires sharing of data, but the sharing of data exposes private and other sensitive information. So we sanitize or anonymize the data, and I'm going to use the two terms as synonyms, although there's really a slight difference between the two. The key point to take away from this talk is that anonymization is a problem of threats, risks, and relationships, with some of each being unknown. Okay, so it's a good idea to have a particular system model in mind. So here's the system model that I'm using. You have some raw data, and you have some analysts. So they go ahead and analyze it and produce some results. Another group wants access to it to do the work. And so you go ahead and give them access, but you sanitize the data first. They do the same analysis the first group did, and ideally, you want the results to be the same. However, there's a catch to all this. There are adversaries or nasty people, who want to desanitize the data, get out the private information. And so to prevent that, we have some sort of a privacy policy in place. That controls, among other things, how the sanitization is done. But there's a contradiction here. The threat model says what security controls are to thwart those. And a breach occurs when it doesn't work. But since you have personal or other confidential information in there, you want to hide it. And this can cause problems. If it's not hidden, this can cause problems not only for the folks who have the data, but also for the subjects about whom the data refers. And so it's very important that that type of information be hidden. But on the other hand, we have utility. Other parts of the information have to be exposed for analysis. I've done a lot of work in intrusion detection, and we love getting raw network traces, so we can analyze them and test our tools. Medical data, for example, is used in epidemiological studies and many other types of studies. Okay. By the way, with intrusion detection too, removing the packet bodies is what is often done, but that still enables traffic analysis from the headers. Okay. So there are two things. So we want to know, what do we mean by disclosure? I'm a nut for defining the terms that we're using. And there are actually two definitions of this. The first one was done by Tordelenius in a 77 paper, where he said that a disclosure takes place if you release some anonymized data, and from that you can determine the value of an attribute more accurately than if the data were not released. It's a great definition, it's an ideal, but it's not practical for various reasons. Cynthia Dwork came up with another one, which is much better and much more widely used, namely that the risk to privacy should not substantially increase as a result of participating in a database. Okay. And she formalized this in differential privacy. And here's the formal definition. You know, after all, any good computer security talk needs to have some math in it. But the concept really is simple. We have two databases. A record in both databases has a different value in one of the fields of interest. One is the anonymized, the other is the non-anonymized. The equation simply says that the differences in the probabilities of determining the information of the unanonymized data set, knowing only what's in the anonymized data set, can be made arbitrarily small. That's what the epsilon, the e to the epsilon refers to. Okay. Now, whenever a scientist says arbitrarily small, you have to be careful because they're not saying it can't be done. They're saying it's very hard to do. Okay. And Cynthia Dwork proved the theorem that drives this home. The theorem says that when an anonymized data set is released, there's always external information that can be combined with the released information that enables someone to figure out the hidden information, except in the most trivial cases. So let's take a look at how this can be done, and I'm going to use Netflix as an opening example. Netflix in 2006 held a contest to see if their recommendation system could be beaten, or could be improved, I should say. The training corpus had over 100 million records in it, with user ID anonymized, the date anonymized, changed somewhat, the movie and the rating. And the records covered over 17,500 movies and about 500,000 users. Okay. So you can see the top rectangle, how they did the anonymization. Okay. That was what the people trying to build better recommendation systems used. But a couple of people at the University of Texas got curious. They realized there's a public source for all that information as well, the Internet Movie Database. And so what they did was they took data from 50 users' records, and from that started comparing the data in those records to what was on the Internet Movie Database. And as a result, they claimed to be able to de-anonymize at least one of the users involved. And here, basically, the way they did it was, if you look at the first one, there's no match. The movie is Titanic and the stars are wrong, so users 6946 is not Celia. But if you look at this, the date is within statistical tolerance, and everything else is the same, so the record match. So they used external information to de-anonymize the anonymized information. So this brings us to our threat model. What's the threat model? Well, first of all, we never assume the adversaries have access to the raw data. Otherwise, why is this a problem? In some cases, we'll assume that the adversary can inject things into the data without knowing what that data is, and sometimes that can be used to derive structure or other information about the data. But for this talk, I'm simply going to assume that the adversaries have access to the sanitized data and we're not able to corrupt the original data as it was being saved. And in fact, that's usually what people do assume. So given the Netflix results, which used external information, the obvious question is, great, what information does the adversary have access to? Well, before 1993 maybe, that was actually a very good question because the information was not easily available. If you wanted to get information about someone, for example, you typically had to go to where they were or hire someone to do that and look through court records, county records, things like that. But then came the World Wide Web. And all of a sudden, all that information suddenly became widely available. So it's not realistic to say, well, let's figure out what they have available. It's probably much better to say, well, let's look at the relationships among the data records that might allow someone to determine the hidden information and then try to hide or break those relationships in some way. Okay. For example, if Paul works late in the evening, and all someone has is a record of times when the card reader recorded someone going in, they'll be able to figure out what Paul's card is. And I'll give you a very good example of that in a much more sensitive environment later on. Okay. There are other aspects to the model as well. Temporal. There are two types of temporal issues here. The first one is that if threats don't remain constant, they evolve. For example, in the United States during the Great Depression in the 1930s, many people joined the Communist Party because they saw it as a beacon of hope for the future. But in the 1950s, that often came back to bite people with the House Un-American Activities Committee and Senator McCarthy's committee and a few other committees that took any membership in the Communist Party at any time as meaning you were working for an adversary, in this case, the Soviet Union. And unless you named names, you were basically a traitor. But now, that ended around the late 50s, early 60s. Now, if you know someone who's a communist, you may think, well, okay, it's good they can believe that in our system, or maybe they're a little odd, but you're not going to see them as a threat to the United States. So the threats change. The other aspect of this that's important is if I release a data set and then I release another data set later on, individually you may not be able to de-anonymize them. Put them together and you might be able to. This becomes particularly touchy when two different organizations have the same data and they don't coordinate what they're hiding. Things like that have, in fact, happened in the past. The other issue is what can you derive from the data, and sometimes it's not really obvious. A friendly attacker cracked a large number of passwords at a major university, and it turned out that many accounts with male names had as their password variants of female names like Barbara 1 or Katie asterisk or things like that. Further, many accounts with female names had male names, or had a variant of male names as their passwords. So from this, he could build up a pattern of who was dating whom, which is not something you would normally expect. And he did check with the people. Everybody knew him and trusted him, so they basically found out that that was correct. Okay? So what this really means is the threat model has to be complete and accurate, and it's very hard to get to the complete model. Now, the Netflix data used relationships that were very obvious. The IMDb had data similar to Netflix, and the relationships were there. So it was a direct construction. However, the relationships are not always that direct, and in fact may be very mysterious. As an example, if you want to hide names in a database that has names, phone numbers, social security numbers, zip codes, dates of birth, and gender, you might think it's enough to hide the name and the phone number and the social security number. Unfortunately, it's not. LaTanya Sweeney, working at Harvard, showed that about 87% of the households in the United States could be uniquely identified by those last three, the ones in parentheses. Amusingly, a couple of years later, some people at Stanford did a similar thing, and they basically said, nope, she's wrong, only 63%. So it was still a very large number from a relationship that one would normally not think of. This, by the way, is where deep learning comes into play, because it can often show relationships that you don't know about or that you wouldn't have thought about. Now, as far as things existing, AOL is a very good example of this. In March to May 2006, they collected search records, and then they released them, anonymizing all the users. They put it out on Friday night at 5 p.m. By the way, don't ever put anything on the web at Friday night at 5 p.m., okay? When people came in on the Monday morning, they immediately ordered it pulled off the web. So the data was gone, right? No, you don't forget things on the internet, okay? The first thing was some reporters from the New York Times got very curious about how safe this data was. Could they de-anonymize it? And so they looked through the records and found user 44177749 had a lot of search records in there. And it was about landscaping in, around Lilleborn. Many people had the last name of Arnold and a number of other characteristics. And from this, they flew down to Georgia, went through records, and found that the lady was named Thelma Arnold. And they know this because they knocked on her door and asked her if these were her queries. And she said, yes, and I think I'm going to unsubscribe from AOL now. Okay. So here's using external data. By the way, AOL stalker. A few days after it went down, the AOL data went down, AOL Stalker came up. It had all the data there, so you could perform your own search queries. And I know that slide is very hard to read. It's a screenshot, but I blew up a couple of lines there to show you the sort of information that AOL Stalker has. By the way, AOL Stalker is no longer around. Go to web.archive.org and you'll find it. So nothing really leaves the internet, okay? This screenshot shows what happens when you search for a particular user, in this case, the same one as the New York Times reporters did. You get how many pages they viewed, how they rated the links, the IP addresses and times when they viewed, search query, and if they click through, you'll get the URL they clicked through as well, and the ranking of that URL. Now, this example illustrates a couple of points beyond don't put things on the internet that you expect to take off, okay? First of all, the way it was de-anonymized involved absolutely no mathematics or computer science. Basically, they simply looked for external data that matched the release data, and from that they could build a profile. The relationships of the data in both the released information and the external information enabled the reporters to put them together. Alone, neither of them would have been useful, but together they were both very useful, and it was sufficient to identify the user. So this was an indirect relationship. But it was a little bit more spooky than that. Among the queries the user asked were things about nicotine addiction, emphysema, liver problems, and a couple of other things. And so they figured she was going to be an asthmatic smoker who had health problems. When they interviewed her, she was the perfect picture of health. It turned out she was a retired nurse and she had been doing web searches for her neighbors. So that's an example of drawing the wrong conclusion from the data. Okay, now these examples, and the one I'm going to give you next, shows the need for a complete and accurate threat model. Okay? It's accurate because you want to ensure that you handle the data that's considered, that you consider serious and you don't want released. And also the data that the people who the data is about don't want released. That's something that's often overlooked, okay? You want it complete for that reason. You also want it accurate, and you want to ensure that people can't draw the wrong inferences, because again, with Thelma Arnold, it was very harmless. But in other cases, people may draw inferences that are very damaging to the subjects of the data or to you, and you need to be aware of that possibility. Now, as Heather said, one of the areas I work in a lot is elections. And in the United States, elections have certain properties. Basically, they use a secret anonymous ballot. That means not only can no one link the ballot to the voter cannot prove how he or she voted. The reason for that is, first, they don't want you to sell your votes, and secondly, they don't want two large, ugly people coming by saying, vote our way and prove it or we'll rearrange your kneecaps, okay? So that information is considered very, very sensitive. Well, in Ohio, when you go to vote, you walk in and you identify yourself. I don't remember if Ohio requires ID. I know that California doesn't. And they sign you in on a poll book and put in the time you walked in. Then you get the ballot and you vote. In Ohio at the time, this was done on an electronic voting machine, and it printed up a paper copy of your votes. This is called a voter verified paper audit trail. And among the things it put on there was a timestamp. Now, it turned out at the time, the ballots were public record because they didn't have any names or identifying information on them. And the poll books were public record because they didn't have any information about your ballot. A couple of researchers did the equivalent of a Freedom of Information Act on Ohio and got both of them. And then they started matching up the times for the poll books with the times on the ballots. And that gave them the names of voters. And the paper's really both amusing and terrifying because they described how people voted. And in one case, they said, the name was not Jones, but I'm going to use it, that Mr. and Mrs. Jones may be very uncomfortable hearing that Mr. Jones voted this way and Mrs. Jones voted this way, the opposite. So from that, they were able to derive information. The point here is that external requirements may make anonymization very, very difficult. By the way, the Ohio solution was to make one of them, and I don't remember which, no longer public record. Okay. So where does this go? Well, basically, what can we do? Can we do anything other than throwing up our hands and saying, we can't do this? Well, we can reevaluate how we anonymize the data. Ask how likely it is that an adversary could uncover the relationships in the data involving the fields we want to anonymize. Specifically, what information would they need? If the information is very closely held and you're certain of that, that's one thing. But if it's at all public, you should assume that the adversaries have full access to it. What might an adversary want to infer from the data? You know what you don't want them to infer, but what else might they infer that's damaging to you or to the people, or that might be damaging? So in other words, ask what can be inferred, what would people be able to discover? Okay? And also pay particular attention to false inferences, because those can often be much more damaging for people than if the anonymized data is released. And probably the biggest takeaway from this is to realize that anonymization is not simply a scientific or technical problem. It's a social problem, it's a political problem, it's an organizational problem, and it's a human problem. And all of those have to be taken into account when you do the anonymization. And a parting thought, many people see privacy as an essential human need. And the people who want to deny privacy to others often insist on keeping it themselves. So I think the great Russian playwright Anton Chekhov said it best. The personal life of every individual is based on secrecy. And perhaps it is partly for that reason that civilized man is so nervously anxious that the personal privacy should be respected. And this was written in the early 1900s, if I remember correctly. Thank you.